Good day, lighters. Welcome to the Graceful Light channel. My name is Bongani and I'll be your facilitator for more sessions that are to come to this channel. This channel is developed to assist electrical students that are at tertiary level. It is also developed to assist your electricians, artisans, technicians that are dealing with their day-to-day problems in the field. So you are welcome. Welcome to the channel. Use us, subscribe, also comment. We also have our WhatsApp number, which is 065 545 3217. You can send us questions to this number that you would like us to resolve, or you can send us your problems that you have in the field that you would like us to resolve. There's a saying that says that a candle loses nothing by lighting another candle. That's exactly what this channel is for. We are here to give you light information about the light that we have in terms of electrical engineering, and we are hoping you viewers and the subscribers, you will light others that are in need of light in terms of electrical engineering. That's why we are calling you viewers and the subscribers lighters. So welcome, use us, subscribe. As we can see that during this pandemic, it is hard for the lecturers to impart knowledge to the student, and it is also hard for those who are already in field to attend contact learning classes to improve their knowledge. So we are saying we are here. Use us, use the channel, subscribe, and also comment. Today's session, it will be about three-phase transformers. We will be doing the calculations on three-phase transformers. We will be looking at the difference between your line quantities and your phase quantities. We will also be doing a calculation on your vector groups. So if you are interested, please stay tuned up until the end of the session. I hope we'll work well together. Thank you. Let's start with the presentation, lighters. This presentation is about the basics of transformers. And the learning outcome of this session here is to demonstrate knowledge of transformer application, and it is to solve problem calculation involving transformers. So the purpose of transformers, this is not to say that that's strictly or the only purpose of transformers. These are few of the purposes that we've mentioned here. It is to step up or step down the system voltage. It is to obtain neutral for earth referencing. It is to obtain electrical isolation between two electrical systems. And then we'll also be dealing with the vector group. That is your delta vector group. That is your delta star vector group, your star delta vector group, and your star vector group. What we'll be looking at specifically in this vector group here is your relationship between your line quantities and your phase quantities. It is said that in the vector group, in your delta vector group, that your line voltage is equal to your phase voltage, and your line current, it is equal to the square root 3 of phase current. The way to solve this is that if you can prove as lighters, if you can only prove one quantity, like in this case we are talking about the voltage quantities and the current quantities. So if you can prove one of the quantities are equal, then the other one will assume it to be the square root I line, the line quantity will be the square root of the phase quantity. Let's go and look at what I'm talking about. So that your delta configuration, so we said here that in the delta configuration, our V line is equal to the square root, our V line, it is equal to the V phase, and then our I line is equal to the square root of I phase. So if we look here at the drawings, let us try and see why do they say that our V line is equal to V phase. So we must know that the line voltage, it is the voltage that is measured between two lines. Therefore, in the presentation here, we have your red line there, you have your white line here, and then you have your blue line here. Therefore, the line voltage, we need to measure it between two lines. Your line voltage 1, it will be measured between your red line and your white line. Your line voltage 2, it will be measured between your white line and your blue line. Your line voltage 3, it will be measured between your blue line and your red line. So if we look at the phase voltage, the phase voltage, it is the voltage that is measured across your phase impedance. In the delta here, those things are representing the phase impedance. Phase impedance. That's the phase impedance for the red phase. That's the phase impedance for the white phase. That's the phase impedance for your blue phase. Therefore, when we are talking about the phase voltage, it is the voltage that is measured across this impedance here, your phase impedance. So if you are looking to the voltage that is measured across the red phase, which is your V red phase impedance, we'll be measuring it across your red phase impedance. If we look here, that is the same as this point here, which is R, and this point here is the same as your W. Therefore, your V red phase impedance is measured between the R line and the W line. And then if you can go again to your white phase impedance, we need to measure the voltage impedance on that one. It will be measured across this phase impedance here, which it means that it will be measured in this point and that point. This point here and that point, this point here, it's your blue line point, and this point here is your white line point. Therefore, your white phase voltage, it is measured across your white line and your blue line. And then lastly, if we look at the blue phase impedance, it is measured across this line. This is across your phase impedance. It is measured from this point and that point. Therefore, your V blue phase voltage, it is measured between this point and that point there, between your blue line and your right line. So as we can see that our line voltage, it is measured across the red line and the white line. Even your red phase voltage, it is measured across the same points. So like I said, that if you prove that one quantity is equal to the other quantity, therefore the other one, in this case we have proven that our voltage line quantities are equal to our voltage phase quantities. Therefore we conclude that our current line quantities, it will be equal to the square root 3 of I phase. We will prove that there's a session that I will do it. For now, we are just doing the summary of this, but I will post a video again about the session that will prove where does the square root of 3 comes from. Why are we saying that our line voltage is equal to the square root of 3 I phase? Let me go to the board later so that I can draw this drawing to start it, so that maybe I can bring some light to you. We will do it together. You can grab a piece of paper so that we can also do it together like us. I'm going to the board now. As we said that we'll be checking the relationship between our line quantities and the phase quantities in the board, in the delta. So that's exactly what we'll be doing now. I'm going to be drawing in the board here the delta connections, and then we will start checking what was the relationship between our line quantities and our phase quantities in terms of the voltage and in terms of the current. The current part one is the one that is a little bit difficult. That's why when we saw that the V line is equal to V phase, then we conclude that our I line is equal to the square root of 3 I phase. Let me draw in the board so that we can understand all together. So that's your delta connection. Then that's your red line, that's your white line, that's your blue line. Red line, white line, that's your blue line. Then that's your phase impedance, which is red. That's your phase impedance, which is white. That's your phase impedance, which is blue. And we assume in this case that the phase rotation is anti-clockwise. We assume that the phase rotation is anti-clockwise. It might be clockwise, it might be anti-clockwise. So now we have to write down the quantities. First of all, we'll be starting with the phase quantities, the phase voltage quantities and the line voltage quantities. Then at the end, we'll be doing your current line quantities and your current phase quantities. So we are starting with the voltage phase quantities now. So we know that for our V line, the V line is measured between two lines or between three lines. So now we will show in the board, we'll start with our first V line. We are starting with the line quantities. So your voltage line quantities, we will have to draw them in our delta configuration here. So your V line 1, it will be measured between our red line and your white line. And then your V line 2, it will be measured between our white line and the blue line. Your V line 3, it will be measured between our blue line and the red line. So let's note them down. We've drawn them, we've indicated where do we measure these V lines in our delta configuration. So let's write them down. Our V line 1 is equal to, we measure it between our red line and the white line. Our V line 2, we measure it between our white line and the blue line. Then our V line 3, we measure between our blue line and the red line. Now that we are finished with the line quantities, we have to indicate the phase quantities, not current. We are doing voltages. We are comparing an apple with an apple. Therefore, if we are doing line quantities, we'll have to do phase quantities in terms of the voltage. Now we'll be checking where do we measure our phase voltage. The phase voltage is measured across each phase impedance. So that will be your phase voltage 1, phase voltage 2, phase voltage 3. It is measured across each phase impedance, the phase voltage. Therefore, that's your phase impedance. The voltage here, we will measure it across here. V red phase is measured across. If you can see here, this point here is exactly the same as your R. Therefore, it is measured across R, and this point here is your W. R and W. And then your V white phase, it will be measured across the white phase impedance. V white phase. Even here, if you can see here, this point here is W, and this point here is your blue line. Therefore, it is measured between our white line and the blue line. And lastly, your V blue phase, we measure it across the phase impedance. V blue phase. Still here, you can see that you measure it here, which is this point is your blue phase, and that point is your red line. Therefore, we measure it between the blue and the red. So let's note down our phase quantities. Your V red phase, we measure it between the red line and the white line. Your V white phase, we measure it between the white line and the blue line. And then your V blue phase, we measure it between your blue line and your red line. So if you can see now, we are looking at the relationship between our line voltage and the phase voltages. Here it's voltage and the phase voltages. Now when we are looking at the relationship between our line voltage and the phase voltage, you can see that your V line 1 and your V red phase, they are measured across the same points. Your V line 2 and your V white phase, they are measured across the same points. Your V line 3 and your V blue phase, they are measured across the same point. Therefore, we conclude that our V line is equal to V phase. That's the first part. We've established that in a delta connection, that our V line is equal to your V phase. Now we will look at the current quantities. In a delta configuration, it is a little bit hard to identify that your IL is equal to the square root 3 of I phase. You will not be asked to prove it. You must just know it, but there is a session that I'll be holding about that part of how to prove your IL is equal to your square root 3 of I phase. So let's show where do we measure our line current and our phase current. Therefore, here this will be our I line 1, here this will be our I line 2, here this will be our I line 3. Why we are saying this is the line currents is because they are measured in the lines. So then let's go and check where do we measure our phase current. This will be our I red phase, and this will be our I white phase, and this will be our I blue phase. Remember now we said that if the rotation is anti-clockwise, then it means the current inside the delta connection, it is flowing from here to there. So now let us apply engineering terms in trying to resolve the issue of I line 1 and your red phases. So if we are looking at this point here, if we are looking at that point, we see that our I line 1, this one is coming and this one is coming that way, and then they make a total of IR. Therefore, that's a Kirchhoff's law. So if you are looking at this point to this, these two are coming to that. Therefore, it will mean that our IR is equal to our I blue phase plus our IL1. This is only in terms of the magnitude. Otherwise, if we then include the phasor diagram, your angles, then it becomes complicated. That's why I was telling the lighters that that session we will start exactly on the next session. We'll start exactly on this part here of the Kirchhoff's law. Otherwise, for this session, it gets too complicated to prove that your IL is equal to the square root 3 I phase. So, because we couldn't prove this one, you can see this one is the difficult one. Therefore, we don't use that formula here. We use the formula of IL is equal to the square root 3 of I phase. Remember, lighters, this is proven. That's why I'm saying that in the next session, I will prove it to you. But if you want it now, it's difficult to prove it. You see, it's giving you the rank values. We don't use that now. We know that if we prove that our VL is equal to V phase, then our IL is equal to the square root 3 of I phase. I promise you again, lighters, that for this, I will do a session for it. Stay tuned, subscribe to the channel. Whenever I'm uploading that new video that is showing the relationship between these two, you can also be notified. Therefore, we don't use this formula here. This formula there on top is invalid and it's unfinished. So the formula that we are using is this one of IL square root of 3 I phase. That's why I was saying, in short, if you can prove that your VL is equal to your V phase, you just conclude or you take it that your IL is equal to the square root of 3 I phase. Let's go back again to the presentation so that we can finish with the presentation. We will also be doing the exercises. Stay tuned for more. Welcome back to the presentation again, lighters. Now in this time we'll be looking at our relationship between our phase quantities and our line quantities in a star configuration. Remember, on our delta configuration, we've proven that our V line is equal to our V phase, and then our I line is equal to the square root 3 of I phase. Therefore, in the star, we say that our I line is equal to our I phase, and the V line is equal to the square root 3 of I phase. Remember, we said that the shortest way, I am still repeating again that I will prove it. The shortest way is to prove that your line quantity is equal to your phase quantity in terms of voltage and current. Then you will assume, or you will conclude, that the other line quantities is your line quantity is equal to the square root of the phase quantity. In this case, the previous one we did the delta. Now in this case we are going to do the star. So let's look here. If we measure our line voltage, it will be between our red line and the white line, our white line and the blue line, and then, or it will be between our blue line and the red line. And then if we measure the phase voltage, remember I said that the phase voltage, it is the voltage that you measure across your phase impedance, that is inside the transformer, your phase impedance. Therefore, our V phase in this case here, it will be measured between your red line and neutral, because that's the point here, your neutral point. So our phase voltage in the star is measured between your red line and your neutral. And then if we look at our current quantities, your current is flowing from your transformer to your load, is coming back to the neutral, and then is going back again to your load. Now this current that is flowing here through your phase impedance, if you can look, it is the same as the current that is flowing through your line here. Now we therefore conclude that in a star, our I line, it is equal to our I phase. And then if you can look here as well, that the current is coming here, is flowing here, is the same current that is flowing into your line. That's your phase current here, it's indicating your phase current, and that's your line current. So it is the same, it didn't change. Therefore, if you can prove that our line current is equal to our I phase, therefore in terms of voltages, your V line, it will be equal to the square root 3 of V phase. I'm gonna go to the board again and try to explain these letters. Please stay tuned, stay with me. So I'm going to go to the board and try to explain this. Thank you. Now let's look on the board concerning the star configuration, that how can we check the relationship between our line quantities and the phase quantities. We will be drawing now the star configuration on the board, and we will check. Remember that we said if you can prove that your phase quantity is equal to your line quantity, then the other formula will conclude, like in this case, because before we did the delta configuration, and we've seen that in the delta configuration that your V line is equal to your V phase. Then we concluded that our I line is equal to the square root of 3 I phase. Now in this case, I think because of it's a star, we will then have to prove that our I line is equal to our I phase. Then we will conclude that our V line is equal to the square root of 3 V phase. Remember, as I mentioned, I keep on repeating this, that I will do a session on where did we get the square root of 3. So for today, we will just prove the formula so that we can apply them in the questions, so that we can apply them in the field when we have to do calculations in the field. So now we'll be doing the star configuration 1. So this is the star. So we are then assuming that our star configuration will be on the secondary side or on the low voltage side. Therefore, the indications, our red line, white line, blue line, we will do them using the small capital letters. Therefore, this will be our red line, this will be our white line, and this will be our blue line. In the star, there is your neutral point, and then your neutral point is earthed in the star configuration. Therefore, let us populate our information in this star configuration. We'll start with our line quantities. Remember, we compare an apple to an apple, which will be doing the voltages. Now we'll draw our line voltages. Then after that, we'll populate our phase voltages. So now we will be doing our line voltages. Remember, your V line is a voltage that is measured between two lines or three lines. Therefore, in this case, our V line 1, it will be measured between our red line and white line. And then our V line 2, it will be measured between our white line and our blue line. This is a mistake. It shouldn't be a capital letter, it must be a small letter to indicate that this is a secondary or the LV side. Therefore, our V line 2, it will be measured between our white line and our blue line. And then the last line voltage, it will be our V line 3. Our V line 3, it will be measured between our blue phase and our red phase. That's our line quantities. Let's write them down. Our voltage, line quantities. Our V line 1, it is measured between your red line and your white line. Our V line 2, it is measured between our white line and your blue line. And our V line 3, it is measured between our blue line and our red line. Now let's look for phase quantities in terms of the voltage. Remember, I said that the phase quantities is the quantities that you measure across the phase impedance or across the coil of the transformer. So in this case, if you can see here, across the red coil, let me say that's your red, that's your white, that's your blue. So if we measure across this coil, then we get our phase quantities. Therefore, the phase quantity, your voltage phase quantities, if we measure across the coil, we will measure it between your red line and your neutral point. Therefore, your V red phase, it is measured between the red line and your neutral point. And then your V white phase, it will be measured between your white phase and the neutral point. V white phase is measured between our white phase and the neutral point. And then now we have to measure the V blue phase. We just extend this neutral point here, still neutral. So our V blue phase, we measure it across the phase impedance. Therefore, it is measured here. So that's our V blue phase. It will be measured between the blue line and your neutral point. Therefore, let us write our phase quantities. So we indicate our phase quantities, V phase quantities, which is our V red phase. It will be measured between our red line and neutral. Our V white phase, it will be measured between our white line and neutral. And then our V blue phase, it is measured between our blue line and neutral. Now if we look at the relationship between our line quantities, our phase quantities and our line quantities, these ones we cannot say they are the same. If you can look here, we measure our V line 1 across the red line and the white line. And our V red phase, we measure it between our red line and the neutral line. So they are not measured in the same place. Therefore, in this one, remember I said we have to prove that our phase quantities and our line quantities are equal. Then the other one, we assume it will be your V line is equal to your square root your phase quantities times your phase quantities. Therefore, these ones, since they are not equal, we don't measure them in the same place. Therefore, we'll conclude that in this case, then our V line will be equal to the square root of 3 V phase, because we don't measure them between the same lines, because your line quantities, we measure them between your lines, and your phase quantities, we measure them between your line and your neutral. In the delta, the one that we did previously, we've seen that our line quantities in terms of voltage, they are equal to our phase quantities. Now let's go and look at the current quantities in the star configuration. If we are to populate our current quantities here, we will then see if they are equal or not. Therefore, the current in this case is flowing into your circuit. That will be your I line 1, because it is in the line. And then now, once it's flowing through your phase impedance, then it will be our I red phase. And then the current that is flowing here again from your line, it is our IL2. And then once it flows through the phase impedance, then it will be our phase current. Same applies here. That will be our I line 2. You can also say it's I blue line or I blue phase. Even here, I white line or I blue phase. It depends on the language that you are using. Therefore here, the current that is flowing into the phase impedance, it will be our I blue phase. Now let's look at the relationship between our line quantities and the phase quantities in terms of current. If we see here, the current is flowing from your line, it goes through inside your transformer. It didn't change. There is no path that some other current is going to the other point or what. It's just the same current that is flowing through your red phase, and then this is the point, the neutral, the point of intersections. All these currents, when they come here, they go to your neutral. That's the common point, of which this common point, in terms of electrical terms, this is your node. And we can apply here your KCL, Kirchhoff's law current, which is that the sum of current, the sum of current here is equal to when you add these three currents. But now in this case, we are not concentrating on the Kirchhoff's law. We just wanted to check the relationship between our line quantities in terms of current and our phase quantities. Therefore, we say here, if we see here this current, it is the same as the current that is flowing here. Therefore, relationship between line current and phase current. Phase current. So, if we see here, this current that is flowing in our line, it is the same as the current that is flowing through our phase impedance. Therefore, we can say that IL1 is equal to your I red phase. Here as well, if you can see here, the current that is flowing through our white phase, and of which here I've written it as I line 2, you can say I white phase as well, it's going through I white line. It's going through your phase impedance, it didn't change, it's still the same current. Therefore, I line 2 or white line, it is equal to your I white phase. And then here, I blue line, the current that is flowing in our blue line, I named it IL2, is flowing still the same current as the one that is flowing through your phase impedance, which is IB phase. Therefore, IL3 is equal to I blue phase. Therefore, we can conclude by looking at the formulas on the top and the bottom one. We can then say, in a star, your I line is equal to your I phase, and then your V line is equal to the square root 3 of V phase. In a star, we are concluding now that our I line in the star is equal to I phase, and our V line is equal to the square root of 3 V phase. We will do more exercises so that we can check if we can apply these formulas in exercises and in real environment. I think let's go back again to the presentation so that we can conclude with the presentation. Thank you. Welcome back, lighters. Now let us look at the transformer, the picture of a transformer, and we look here, where will we measure our quantities in a transformer, in a real life situation of a transformer. So if we're looking at this transformer here, this is a distribution transformer in one of the substations in South Africa here. So if we're looking here, and we will need to measure our line voltages in this transformer. The line voltage here, first of all, let me give you the information about the transformer. We can see that this side here, the bushings are big, and here the bushings are small. Therefore, this side here is your high voltage side. It goes from this side to that side. It's your high voltage side or your primary side. The bushings here are small. From this side to that side, including inside the transformer to that side, is your low voltage side or your secondary side of the transformer. That's why in the drawings of the vector group there, we indicate the primary side or the high voltage side with capital letters, and the low voltage side or the secondary side with small letters. So in real life situation, it is represented by big bushings. These bushings are big than these ones, therefore this side is your primary side and this side is your secondary side. So if we were to measure the line voltage in this transformer, it will be measured between this line and this line, that line and that line. And then your current will be measured here in this line, that is in your primary side. In your low voltage side or your secondary side, the voltage was going to be measured between this line and that line, that line and this line, and then your current will be measured here. Now the question it will be, where do we measure then our phase voltage and our phase current? There is the impedance or the coils of the transformer inside the transformer that they are going through. I will show you the next picture. I will show you the next picture of how does the transformer look like inside. This next picture here, you can see here on top that these are your bushings, and then these are your coils of a transformer. So your phase voltage and your phase impedance, you can measure it across each phase, but you can see there's a wire here that is going through your bushing, and the other one that is coming here from the same one is going to this phase here and is going through your bushing. Therefore, I can say that this is a delta configuration. If we want to measure our phase voltage, you can still measure it across your line because this is a delta configuration. And then the next transformer that we see here is a pole mounted transformer. It's a different type of transformer than the other one we previously seen. If you can look here in this transformer, these are your HV bushings, and then the small ones here are your secondary bushing or your low voltage bushings. Now lighters, we have come to an end of our session, but please stay tuned because we are about to do the exercises. So stay tuned so that we do the exercises together. Remember lighters, that coming together is the beginning. Keeping together is progress. Working together is success. These are the words that were said by one of the famous guys, who is Henry Ford. So please stay with me lighters. I'm about to do now the examples so that we can do them together. Thank you. Welcome again lighters. At the back of me here is one of the problems that we need to solve together. So if you have a pen and a paper and a calculator as well, please go grab it because we are about to do one of the problems that are here on the board. So let's go and look what is the problem in the board so that we can solve it together lighters. The question here in the board, it says that a 100 kVA 3-phase star-star connected transformer has a turns ratio of 4:1. If the transformer is supplied at 6.6 kV, determine the secondary line voltage. That's the first question. The second question, it says that determine the primary phase current. The third question, it says that determine the secondary line current. So we are about to resolve these questions together. So the first thing that we need to do is to remember what we did in the last sessions, is that we need to draw this star-star transformer, then we need to populate the information in the drawing so that we can know what we are talking about. So let's draw, and you can also take your pen and paper and try to draw your star-star configuration as well. So this is my star configuration. It's a star-star transformer. So if this is a star-star transformer, then this is on your left hand side, this is our primary side, and then on your right hand side, this is our secondary side. So we will indicate our primary side using capital letters and our secondary side using the small letters. So that will be our red line, that will be our white line, that will be our blue line as well. This will be our red line, white line, and blue line. And then we also have a neutral point in both the connection. We have the neutral point. So that's what we do at first. We draw what we were given. Now we need to populate the information. The first information that we have is that the S of this transformer, which is your apparent power, your S is equal to 100 kVA. That's your apparent power of the transformer. And then they mentioned that our N1, the turns ratio, will refer to your N1 and your N2. Therefore, the turns ratio there, our N1 is equal to 4, and then our N2 is equal to 1. Remember the N1, it means that this is your primary side or your high voltage side. And then your N2, it means that this is your secondary side or low voltage side. And then if the transformer is supplied at 6.6 kV, therefore they are saying if it is supplied, this is the transformer, now it is supplied, we get power to this transformer at 6.6 kV. And one of the golden rules that we must remember is that whenever this voltage here, it is not mentioned if it's a phase voltage or line voltage. You take it as a line voltage. You assume it to be a line voltage. In this case, this question didn't state what type of voltage it is. Is it a line voltage or a phase voltage? Therefore, we'll take this 6.6 kV as a line voltage. So we have to indicate it in our drawing. Remember now it says it is supplied. Therefore, this transformer is supplied at 6.6 kV. Then that means your V line. Remember, the V line, it is the line voltage which is measured between line to line. Therefore, your V line, it will be your V line red to white or V line 1, it will be 6.6 kV. Here, your white to blue, it will be 6.6 kV. And your blue to red as well, it will be 6.6 kV. That's the information that we are given. We don't know about the information in our secondary. There's no information that was given for our secondary side of the transformer. So now let's go and look at the question. The question says the secondary line voltage. Then that's the first question. It says that we must come here and look for our V2, which is the secondary line voltage. Your 6.6 kV is your primary line voltage because it was saying the transformer is supplied. Therefore, this is our V1. V1. Your 1, it means it can be either a line quantity or your phase quantity. Therefore, in this case, we have our V1. We are looking for V2. That's the first question that they are asking us. So, first question, they say that we must look for our V2. Therefore, we can use the formula of a transformer that says V1 over V2 is equal to N1 over N2. And then we try and populate. We have all these formulas here, all this information, we have it all here. So now we are just substituting here. Your V1, you can see it is your 6.6, or you can take any one of these. Therefore, your V1, it will be 6.6 kV times 10 to the power 3 over V2. We don't have the value for V2, so we are looking for that V2. And then your N1, this is our N1, which is 4. So we write our N1 as 4, and then our N2 is 1. We write our N2 as 1. Therefore, let's work together, let us, to look for the value of V2. I'm taking out my calculator. Please also take out your calculator as well, so that we can work the value together. I find my value of V2 to be 1.65 kV. Please let us do your calculation as well, so that you can see if you are getting the same values. So my value of V2, it will be 1.65 kV. So we go and note it down to our drawing here, that our V2 is 1.65 kV. Notice that our V2, we measure it between line to line, and it was not mentioned in the question. Therefore, this voltage here, we take it as a line voltage. So it is a voltage that is measured between line to line. So now let's go to the second question. The second question is saying that we must find out what is the primary phase current. The primary phase current. Therefore, we go and we indicate our primary phase current. Primary phase current. No, it says phase current. Therefore, we have to draw it in the phase. Primary phase current, primary phase current, primary phase current. Any of these current will be the current that we are looking for there. So now we look at this information that we have here. It says we know that in a star, from our previous session, in a star, our I line phase is equal to our I phase. And then we know that our V line is equal to the square root 3 V phase. That is in the star configuration, as we previously mentioned when we were trying to solve, when we were trying to check the relationship between our line quantities and our phase quantities. Now we have to use the formula that we are given to find out what is the value of our primary phase current. We are looking for this value here. We are looking for this value. that is flowing through our phase impedance, which we name it our primary phase current. Therefore, let us look in the board here. What information do we have in order for us to calculate that primary phase current? We know that this is question number 2. We know that the apparent power is equal to the square root 3 VI. Remember, lighters, whenever you are using the square root of 3, you use line values, not phase values. So in this case, I'm going to be using my line value. Then I'm going to convert the line value that I'll be getting here to my phase value using this formula here of the star configuration. So let's go and see if we will get the same answer or if we'll get the correct answer together. We know that our S, it is 100 kVA. Therefore, our S is 100 kVA, square root 3. Our primary line voltage is 6.6 kV. Therefore, our primary line voltage is 6.6 kV. We are looking for our primary line current. Primary line current. The question said we must find primary phase current. But for now, we are looking for the values of primary line current, and we'll change it using our star equation, star configuration equation. So let's calculate together and we see what is the value of our primary phase, primary line current. Let us see what will be the value of our primary line current. I find the value of a primary line current to be 8.748. Please do your calculation as well as lighters so that you can see if you get the correct value of the current, which is 8.748. So what does this mean is that this is the primary line current. This is the value of the current that we've calculated here, which is our I line 1 is equal to 8.748 amps. Remember, while you are still looking at the drawing here, you can see that the current that is flowing from your line into your phase impedance is still the same current, and that's why we said that in your star configuration that your I line is equal to your I phase. Therefore, in this case, we write that in a star configuration, I line is equal to I phase. Therefore, I phase is equal to 8.748 amps. Then we can go and write our value for our I phase here, which is 8.748 amps. You can see, even if you are looking at the drawing, that this is the same current as your I line current. Once it gets inside the transformer, then it becomes your phase current once it's flowing through your phase impedance. Therefore, our primary phase current is equal to 8.748 amps. Now we will be doing the last question, which is question number 3. The last question, it says that we need to find the value of the secondary line current. That means if we are looking on the drawing here, lighters, we need to find the value of the secondary line current. We need to find the value of this secondary line current. We can see here that we have our V2, we have our V1, we have our I1, we are looking for I2. Therefore, we can use that formula of the transformer again that says that V1 over V2 is equal to I2 over I1. Then what is our V1 in this case? We are looking at the drawing. Our V1 is 6.6. So our V1 is 6.6 times 10 to the power 3. We divide it by our V2, which is 1.65 kV, is equal to, we are looking for the value of I2 here that we don't have. We don't have the value of I2, we are looking for it. And then our I1, there it is written there, it is 8.748. Therefore, let us, let's use our calculator together. Let's find out what is the value of our I2. Therefore, I2 is equal to my I2 value is 34,992 amps. I would like you lighters to ensure as well that your value is 34,992 amps, or it can be 35 amps. What I did to get this value, I did the cross multiplication, the mathematical formula. This times this, and this times this, and then you divide by 165. So that's how I got my 34.992. Therefore, the value of our current here, that is flowing here, is 34,992 amps. So I think we've answered all the questions that they ask us to do. And you can see, lighters, that whenever you do a drawing, whenever you draw the drawing, it becomes easy, because whatever you're calculating this side, you have to show it here on the drawing on that side. Then it becomes easy, you know what you are looking for. We are about to do the next question, which is question number 2. I hope you lighters, you will stay with me up until we finish the session. You'll also be doing the next session with me as well. We are about to do the next question, so please stay tuned, lighters, so that we can work together. Now, lighters, we are about to do the second question. It is also here in the board with me. We will check the information as we did in the first question. We will populate down the information so that we can see how can we resolve the question. Remember, every time we do the question, we apply these transformer formulas. We also apply the vector group formulas. Now let's go to the board and see what is the question. The question in the board here, it says that a 3-phase delta transformer delivers 200 amps and 400 volts to a certain load for a turns ratio of 5:1. Calculate the rating of the transformer, the primary line voltage, the secondary phase current, and the primary line current. So now, lighters, we have to draw the information down that we are given here so that we can see if we can solve the question here. First of all, you remember on the first question, we wrote down everything that we see on the board. We wrote it down, so we will do exactly the same with this one. It first says that this is a delta configuration. So we draw our delta, which is our primary side. The delta will be on our primary side. And then we draw, it is a delta, it means the secondary side as well is a delta. So we indicate our primary side by showing with capital letters. That's your line, which is capital letters. It's your red line, your white line, your blue line, your red phase, white phase, blue phase. And then this is our secondary side. We show our secondary side by using small letters. then that's a red phase, white phase, and blue phase. So let's look again in the board. What does the board says, so that we can check how can we populate that information. It further says that the transformer delivers 200 and 400 volts to a certain load. So it says that it delivers, so that means that's our secondary side, because it delivers. That's where we get this power from, on our secondary side. The first question that we did, it was saying it is supplied. It means it was supplied on the primary side. Now it says that it delivers the load to the load. That means those values there will have to indicate them on the secondary side. So remember again the golden rule. They didn't mention that it delivers phase current or line current. Therefore, we take the values that we see there as line values, line quantities. Whenever they don't indicate that a value is a line quantity or phase quantity, then you assume, you take it as that, as like it's a line quantity. Therefore, those values they are our line quantities. That means that your line current and your line voltages. So that will be our line current, which is 200 amps, and then that will be our line voltage, which is 400 volts. So we've written down, and then we have our turns ratio, which is our N1 is equal to 5, and then our N2 is equal to 1. And then the first question says that calculate the rating of the transformer. When there is a question that is like that, that says calculate the rating of the transformer, it means you need to find out what is the value of your apparent power. The rating of the transformer, they do the ratings in terms of the apparent power. Therefore, the first question, it says that we must calculate the rating of the transformer. So it means we will need to find out about the apparent power of this transformer. Let's see how can we find out about the apparent power of this transformer. We know that in a three-phase system that your apparent power, which is S, is equal to the square root 3 VI. Remember again, I repeat, whenever you use the square root of 3, you will have to use your line quantities. Therefore, in this case, we have our V line, which is 400, and then we have our line current, which is 200. And then let's work together. What will be the value of our apparent power? Is equal to the square root of 3 multiplied by 400 multiplied by 200. My value of apparent power, I find it to be 138.564 kVA. Please also do your calculations as well later, so that we can see if we get the same values. So my apparent power in this case, it is 138.564 kVA. The number that you use after the comma, it depends on you, or it depends on the question paper, that if they say they want 2 decimal after the comma, then you write 2 decimal. If it's 1 decimal, it's up to you. After the comma, you write 2 decimal. If they want 2 decimal, you write 3 decimal. If they want 3 decimal after the comma. But I'm using the number 3 because the 3 decimals, because it is more, a little bit accurate to the answer that we are looking for. Now let's go to the second question that says that the primary line voltage. So we have to draw in our drawing here, what value are they looking for? They are looking for the primary line voltage. This is the voltage that they are looking for. Therefore, we can use the formula, the information that we are given here, and calculate our primary line quantities. If you can see, we do have our V2, we do have our I2, we don't have our V2, and we don't have our I1, but we have our turns ratio. Therefore, in this case, number 2, to answer that question, we can use this formula, which is your V1. That's the one that we are looking for, not V2 here. It's your V1. That's the one that we are looking for. We have our V2. We then have your N1 and your N2. So let's look. We populate the information that we have here, which is our V1. We don't have. And then V2 is our 400 is equal to our N1 is our 5 over 1. That's our N2. Then we do the cross multiplication, which is V1 multiplied by 1 is equal to 400 multiplied by 5. Then the primary line voltage, it will be equal to 2 kV, not kVA. If it's kVA, you are referring to your apparent power. It's equal to 2 kV. Please note that, because some of us, they like to make a mistake and then they will say it's 2 kVA. It's not the same thing. We are talking about the voltage in this case. Therefore, it will be 2 kV. Therefore, we write it down here in our drawing that our primary line voltage is 2 kV. That's our primary line voltage, which is 2 kV. Now let us look at the third question. The third question says that we must be looking for the secondary phase current. So if we are going to our drawing here, you will see that your secondary phase current is the current that is flowing through your phase impedance. That's the current. It can be either this one or this one. So it's the current that is flowing through your phase impedance. So in this case, we are looking for your secondary phase current, which is here. We can say that we are looking for your secondary phase current, which is flowing through your red phase. So let's look again on the information that we have here on the statement and also here on our drawing. So the information that we have in our drawing here, we can see that we have your V1. We don't have our I1. We have your I2. You have that's your 400 here. You have your V2. What they want in this case is the current that is flowing through the secondary. In the secondary side, it's written there, the secondary phase current. Therefore, we do have our first secondary line current. We can then use this formula here because we have our secondary line current, then we need our secondary phase current. That's the formula that we can use, which is L is equal to the square root of 3 IP. Our line current in this case, it is 200 amps. Our line current in this case, it is 200 amps, is equal to the square root of 3 multiplied by I phase. Therefore, our I phase, it will be 200 divided by the square root of 3. Let's use our calculators again, writers, to see what will be the value of our secondary phase current. Therefore, it will be 200 divided by the square root of 3. My value that I get here, it is 115.470. Please ensure again, lighters, that you get the same value. it is 115.470 amps. That means it's our secondary phase current. So we need to go and draw it or name it in our circuit here. So this current that is flowing through our phase impedance here, it is equal to 115.470. And then the last question, it was saying that we need to find our primary line current that we don't have. We have our secondary line voltage, we have our secondary line current, we also have our primary line voltage. Therefore, we can use the formulas of a transformer, which is the last question, which is question 4. We have your V1 over V2 is equal to your I2 over your I1. My I2 in this case is 200 amps, and then I don't have my I1 that we are looking for, the line current. Therefore, that's I1. And then my V1 in this case, it's your primary line voltage is equal to 2 kV, and then my V2 is your line voltage, which is equal to 400 volts. Therefore, we do cross multiplication. It will be your I1 multiplied by 2 times 10 to the power 3 is equal to 400 multiplied by 200. And then my I1, it will be my I1, I find it lighters to be 40 amps. Please also do your calculation and ensure that you get 40 amps. So that's the value of my I1. Then I'll have to go and indicate it here in the drawing. So my I1 here, it will be equal to 40 amps. Remember, it is the line current. That's why I'm drawing it in your line, because it has to indicate that it is your line current. Now I think this is the end of the session for today's questions. Please stay tuned. I'll also leave another question for you lighters. Also do the question that I will be writing down in the next video. It will be the question that I would like you lighters to do it on your own at home, to do it with your fellow students, to do it with your fellow colleagues. Please work together. Like I said when I started, that we are here to light others as well. So the next question that I'll be placing on the board here, I would like you lighters to do it at home. Whenever you got the answer or the solution, please send it to our WhatsApp number, which is 065 545 3217. I will also be doing the next question in our next session. When I'm uploading a new video, we will start to do that question as well, so that you can see if your answers are as mine. We are looking at each other now. We are not looking at the memorandum. Please let us stay tuned for the next question. Thank you. We have come to the last part of our session for today, lighters. The last part, it is about a question. I'll be giving you lighters a question that you need to solve with others so that you can light them, or you need to solve it with other fellow students, other co-workers. So this is the last part of our session. Let me just move aside so that you can see what is our last part. It is a question that I would like the lighters to do at home, and whatever answer you got, please send it to our WhatsApp number, is 065 545 3217, so that we can see if you got it right. We'll also be doing this on our next session with you lighters. So the question here says that a 3.3 kV 380 3-phase delta star connected transformer delivers 20 kilowatts to a certain load at a power factor of 0.9 lagging. They then want you to resolve the following: the primary phase voltage, the secondary phase voltage, the secondary phase current, the primary line current, the rating of the transformer in kVA, and the turns ratio of the transformer. So That's the question that we need you guys to resolve. You lighters, you need to resolve the question. You can also send it to our WhatsApp number, which is 065 5453217. That's the answer that you'll be having. Please send it to our WhatsApp. Please don't forget to subscribe. Users, we are here during this pandemic. We can work together. Remember, lighters, that working together is progress. Keeping together is success. I hope you enjoyed the session. I'll see you in our next session for the future. Thank you, lighters. Enjoy and bye.